In this section, we'll cover the tools and techniques for the quantitative process. Here we have data gathering and representation techniques, and quantitative risk analysis and modeling techniques. For data gathering and representation techniques, we have interviewing, probability distributions, and expert judgment. We've talked about interviewing before. Remember, it includes project team members, stakeholders, and subject matter experts, and it's used to determine the probability distribution to be used for analyzing the information. The technique determines your questions in the interviews. You also want to document how the interviewed people decided upon the risk ranges, the criteria for categorizing risks, and the results of the interview. Probability distributions are a mathematical way of expressing the uncertainties in values, and it gives a reasonable spread of the possibilities. An example would be the durations of schedule activities and/or costs of project components. The types of distribution models are normal, log normal, triangular, beta, and uniform distribution. These can be displayed as graphs, which represent the probability and the time or cost elements. In the case of triangular distributions, we find that they're based upon the 3-point estimate: pessimistic, most likely, and optimistic values. These values are gathered from interviews and used to quantify risk for each work breakdown structure element. For normal and log normal distributions, we find that it uses mean and standard deviations to quantify risk. This also requires the 3-point estimate: pessimistic, most likely, and optimistic values. For expert judgment, the project manager would want to validate the data and the techniques from within or outside the organization. There are 4 quantitative risk analysis and modeling techniques: sensitivity analysis, expected monetary value analysis, decision tree analysis, and modeling and simulation. Sensitivity analysis analyzes the potential impact of risk events on the project. It determines which risk events have the greatest potential for impact and examines all uncertain elements at baseline values. It displays this data using a tornado diagram. In a tornado diagram, each bar represents a sensitivity variable. It displays the low and high value possible for that element, and it appears at the top of the diagram if the variable has the biggest impact. It ranks the other variables according to their impact, largest to smallest. It provides a quick overview of those risks with the biggest impact on the project and determines the stakeholder risk tolerance levels as well. As you can see, each sensitivity bar displays the low and high value possible for that element. You'll not have to know how these values are calculated for the exam, and it's too complicated to discuss here, but you should understand the circumstances for using this type of diagram and why it would be chosen. Expected monetary value analysis calculates the average anticipated impact of the decision. It's calculated by multiplying the probability of the risk by its impact and then adding them together. It's used in conjunction with the decision tree analysis technique. Positive results generally mean the risks being assessed pose opportunities to the project, and negative results indicate a threat to the project. Decision tree analysis displays the sequence of interrelated decisions and the expected results of choosing one alternative over the other. Multiple choices are displayed by the decision tree, branching out to show the anticipated results of each choice possible. It uses the expected monetary value calculation to determine the expected monetary value of each decision. As an example of a decision tree, we look at the high risk to the project and what can be done about it. Multiplying the expected monetary value of the decision by the probable results will give a value to the decision and its options. Decision trees can be quite complicated and certainly not as simple as this one. Here, the investment in process improvement looks to reap the highest value. Let's walk through this example. To mitigate the risk of the release management problem for this project, two choices have been developed. Choice number 1 is to invest in process improvement where the setup costs are $100,000. Choice number 2 is to invest in a tool with no process improvement activity at a lesser cost of $75,000. The worst case scenario for choice number 1 is that failure has a probability of 30% and an estimated $75,000 impact in rework. However, on the positive side, the past scenario has an 80% chance of success and no impact costs. For choice number 2, the worst case scenario is a 70% probability of failure, which would result in a $75,000 cost in rework, and the best case scenario is a 20% probability of success with no impact of costs. In choice number 1, when you multiply the 30% probability of failure by the $75,000 in cost, you get an expected monetary value of $122,500. This calculation is performed for each possible outcome. In this example, choice number 1 would be selected as it would be cheaper to invest in process improvement with the higher initial cost, but with the higher chance of success. Modeling and simulation is used for project schedule risk analysis and cost analysis. It allows a translation of potential risks at specific points in the project into their impacts, allows a determination of how much the project objectives are affected. The Monte Carlo is an example of a simulation technique. Analysis is replicated many times using cost or schedule variables. Every time the analysis is performed, the values for the variable are changed using a probability distribution for each variable. It evaluates the project, not the tasks. This concludes the topics of tools and techniques for quantitative risk analysis. In the next section, we'll cover the outputs of this process.